Hello and welcome to the next video in the series of Physics at Home. Today we are going to calculate the acceleration due to gravity. And what is acceleration due to gravity? It is the rate at which the velocity of an object changes under the influence of gravity. So an example of that is if you have this car, let's say, and if you let go, then it started to change its speed or velocity more appropriately at a rate of 9.8 meters per second square. And today we are going to try and calculate if it is possible that to see if we can have this car roll down a ramp, and then as it goes down we can time it, as in how long it takes to go from the top to the bottom of that ramp. And as we can guess that it is going down because gravity is pulling it down, right? Now it is not going straight down, but at an angle. So there's going to be a little bit of trick involved, okay? And we'll see how it works. Now to work this out, we need to create a ramp. So some kind of household item is what we need. Okay, so here I have a block. If we put it here, okay, or something like this. Yeah. Now there is a little bit of tilt there, right? Now it's not on the floor, and we know that, so car stays at that point. But if I tilt it a little bit, so as you can see, the car is trying to move, but it's still hesitating there, right? Now the reason being that there is a little bit of friction here in these wheels. Okay, so in my trials, what I realized that at least at an angle of 10 degrees or higher is when you actually start seeing good results, because then you start to overcome the friction. Okay, so to make it about a 10 degree or higher tilt, I'm going to use this soapbox, something like this. Put the block on top of it, and then put this one here like that. Now I want to make sure that all of these pieces stay firm as the car rolls down. Okay, so we could use a tape to tape everything down here. Now before I do that, I need to measure the length of this ramp here, or this track. So I have a ruler, and it goes from 0 to 30 on the other side, as probably you can see, yeah, 30. So if I place the 0 here, okay, then 30 is right where you can see that mark. Okay, so 30 is right here, and then you can start counting from 0. So add about 22. So 22 plus 30, so total 52 centimeter is the length of this ramp. Okay. Alright, so let's make the ramp now. Get a tape and create a loop out of it. Stick it on the table or whichever surface you're using. I just want to make sure. Yeah, I think this is pretty good. So this stays here. Okay. Another piece of tape for the block. Alright, so it's there now. One piece of tape at this end of the track. I'm going to lay it down right here. Now, depending on what tool you use, maybe like a can of tuna or a book or something, to create this height for the ramp, I just want to make sure, okay, word of caution, that you want to make sure that the ramp is not tilted one way or the other. Otherwise then when the car slides down, it will be rubbing against the railings here, right, so to speak. So I want to make sure. Okay, so it's nice and flat. One last piece of tape at the bottom of the ramp. Okay, so I have it. Now we need one more support somewhere in the middle, because this is a pretty soft plastic here, so it would bend, right? So what I'm going to do, just kind of barely, okay? I don't want to over push it, so just make sure that it is nice and firm. A little bit more maybe, yeah, okay, now it's fine. And now we are ready to run this experiment. So what we want is the rear wheels of the car sitting at the end of this beginning of this ramp, and the car is going to slide down, and then there will be two clicks. First click will be the front wheels landing on the surface here, and then the second click will be the rear wheels landing on the surface here. So the first click is somewhere where I'm going to time it using my stopwatch, so that's when I'm get alert, and then second is when I would push it. So click is I would know. The second click is where I can stop my stopwatch. Okay, so just as an example, you can hear the two clicks. Okay, alright, so that is how we're going to run this experiment. You can also see it, okay? And then you can see that as it goes and then it's about to go off, right there when it goes off, you can stop your stopwatch. So on my old school cell phone here, I've opened the stopwatch app, put the car at the top, and we are ready to run. So 1, 2, 3, go. Alright, so it's 0.74 seconds. Reset, start again. 1, 2, 3, go. 0.71 seconds. And 1, 2, 3, go. 0.74 seconds. Okay, so within 2/100ths of a second, I see 3 readings. So when I take an average, it'll be some number between the two. So if you run this experiment and then you also get readings which are close enough, then you can be certain that there is what is called as reproducibility in your result. So whatever you did in the first trial attempt, you're doing the same exact thing, so as to take the human factor away as much as possible. Not only that, but with the 3 trials, human factor is almost 0. Okay, so we can assign whatever the result is to the pull from the gravity. Okay. So now in the next segment of the video, we're gonna see how to measure or run all of these numbers and calculate the gravity. But before that, I've almost forgot. I have to make sure to measure the height. Okay, so this is 10.5, 10.6, something like that. So about 10.6 centimeters. So height equals to 10.6 centimeter. And so the length of the ramp is going to be the hypotenuse of a right triangle, and then height is going to be opposite to this angle over here. And we will see in the next video how this angle is going to be related to the acceleration down the incline and also the direct pull by gravity. Okay. On this slide here, on the left hand side, we see the setup for our lab. The block here represents the car which was rolling down the hill. Now, since the wheels are too small, we can consider the car to be as close as a situation as a block sliding down a hill with as little friction as possible. The first thing to notice here is that there is a right triangle here, as we can see. And on this right triangle, L represents the hypotenuse. And with respect to the angle theta, the ramp makes with the horizontal, H represents the opposite side. And as we know, sine theta is opposite over hypotenuse. So we can write this down as h divided by L as sine theta. This relationship here is of very importance to us. Additionally, we can see that there is a little red triangle here. This is also a right triangle. This right triangle, the hypotenuse of this is the g. G is the pull from the gravity, okay? The gravitational acceleration. But we know the block or the car wasn't going straight downwards. It was going along the incline. So what we need is the projection of this g on the line or the direction along which this is moving, right? So this is moving along this direction. So we want to know g's projection or shadow along that line, which we can see is the A. Okay. Now with a little bit of trig, we will realize that the angle theta here is the same angle theta here. Okay. So we can write down sine theta, which we know is opposite or hypotenuse, opposite to that angle theta in the little red triangle. Opposite side is A divided by hypotenuse, which is G. As we can see, both the sine theta relationship that we see, they represent the same angle. Hence, we can get this relationship. A over G equals to H over L. Okay. Now, as we know, we already know the length of the ramp and the height of the ramp. Yeah. What we're going to do next is, using kinematics, calculate this acceleration A. Once we get A, then the last thing to calculate would be the G. Okay. So for the kinematics, we are going to use this equation. X equals to x0 v0t plus half a t squared. Now let's see what are the pieces of this equation are. X represents final position of the block or the car, which is right here. X0 is the initial position, which is right here. And we can always say that the block starts from the 0 position. So we can, make x0 as 0. The final position then becomes L, which is 0.52 meters. Right? V subscript 0 is initial velocity, which in our case is 0 because the car starts from rest. A is the acceleration, the rate of change of velocity of the car, which we don't know, and T represents time. This T here is the T average of the 3 trials that we conducted earlier. And this right here is the T average. So for our case, this was 0.73 seconds. Okay. So now that we have all of these pieces together, okay, now we can plug them in and solve. So 0.52 is equals to 0 plus 0 times 0.73 plus half times A times 0.73 square. That gives us 0.52 equals to half times A times 0.73 square, because these two, they cancel out. Yeah. So now that we have all of these, okay, so let's take this another step here with a little bit of algebra. So 2 I want to move to the left, so it becomes 2 times 0.52, and then the 0.73 square also want to move to the left, which gets divided now, 0.73 square. That gives us A. Now if I plug this into my calculator, alright, so 1.9516, that is the acceleration of the car. So meters per second square, this is A. Okay. So now that we have this number, we are gonna plug in into the AGHL, that relationship that we know. Okay, so let's do that. A over G equals to H over L. Again, I'm going to do a little bit of algebra here. I want G to the right and H and L to the left. So L times A divided by H equals to G. Plugging in now, 0.52 times 1.9516 divided by H is 0.106. Okay, again, these H and L numbers are right here, as you see on the top left corner, and that gives me the value of G. So $9.574. So in the experiment that we ran, it tells us that the gravitational acceleration is 9.574. Now this number here is close to 9.8. And how close? Well, we can do a little bit of percent error calculation. So let's do that. Percent error is going to be the experimental value minus theoretical value divided by the theoretical value multiplied by 100. And I want to make sure that I get the absolute value here of the difference. So plugging in, now I get 9.574 minus 9.8, that is the theoretical value, divided by 9.8 times 100, and that gives me Alright, so that gives me 2.3. So my percent error turned out to be 2.3%. Now it's a close enough number. Okay. Now if it was 9.8, then I wouldn't have believed it, because I'm not expecting an exactly 9.8 number, because this is a real life example, right? So there are things that could have affected that value to be away from 9.8. And what could have gone wrong, or what could have caused the percent error, is for you to give it a thought. Okay, so once again, just to be sure that just to reiterate myself, that as long as the theta, or the angle of that ramp, is 10 degrees or higher, then you can expect a single digit error. Lower than 10 degree of angle, you would be probably 2-digit error. Okay, now just for the sake of it here, I tried to calculate the angle earlier, and the theta here was, if you take the sine inverse of H over L, so it's about 11.76 degrees. Okay, so the angle here is 11.76 degrees. Okay, alright, so I hope you enjoyed this video, and next week we will come back with projectile motion. Have a good day.